Hello everyone, my name is Yanxin Long, and I'm glad to present our work CapDet. Currently, the open world scenario mainly includes two tasks: open world object detection (OWD) and open vocabulary object detection (OVD). Although the paradigms of OWD and OVD tasks are closer to the real world, the former cannot describe the specific concept of the detected unknown objects, and OVD can only predict the concepts that appear in the given class list. Under the OVD setting, we mainly face the following two challenges. It is difficult to define a complete list of classes. It can only generate low response values on rare classes. In this paper, we consider a new setting that is closer to the open world and real scenes. That is, we expect the model to both detect concepts in a given classes list and to generate corresponding natural language descriptions for new concepts or rare classes of objects. We propose to unify the two pipelines of dense captioning and open world detection pretraining into one framework. This is the overall architecture of CapDet. The training paradigm of CapDet contains open world object detection pretraining and dense captioning. In detection, CapDet contains a visual language encoder. The image encoder generates region embeddings from detection and dense captioning data. The regression loss and centeredness loss are introduced to regress the locations. The test encoder take the classes concepts as input to generate the embeddings from the EOS token. Then we treat the detection task as a matching task and adopt an alignment loss for the class embeddings and region embeddings. In dense captioning, an additional dense captioning head is proposed to take the region embeddings as input and generate the textual captions for corresponding regions with natural language. Table 1 shows our zero-shot object detection performance on Elvis. We mainly train our CapDet with the backbone swing T on the detection data object 365 and dense captioning data visual genome. Since that clip does not report the performance on object 365 and visual genome, we train that clip on the two datasets under the same settings and denote it as that clip TC here. Comparing the 11th row and 12th row, our CapDet outperforms that clip TC on the same data scale and backbone with an extra simple caption head. Table 2 and Table 3 show CapDet significantly outperforms the latest work TDC by 2.5% on NAP on visual genome and TDC plus ROCSU by 2.08%. For the practical deployment, we propose a simple two-stage ensemble way to stay true to our motivation. Specifically, in the first stage, we execute detection on images among the predefined classes list and treat the proposals with maximum alignment scores among all classes less than a threshold as unknown objects. Then in the second stage, we generate the captions for the unknown objects. To demonstrate the effectiveness of the proposed strategies, we conduct detection on the images with 80 classes of COCO and regenerate captions for the unknown objects. As shown in the figure here, our proposed strategy expands the semantic space of the limited category list and shows reasonable results. Thank you for your listening.